Hello, everyone. My name is Sarah Clerical, and my team members are Matt Takara and Jasmine Chang. We represent an interdisciplinary group of students with backgrounds in architecture and civil engineering who share a common interest in exploring the role of data science in the AC industry and its applications across all stages of the building lifecycle. We found that HVAC systems consume nearly 40% of energy of commercial building operations in the US, depending on multiple factors such as outdoor air temperature, number of occupants, humidity, and ventilation. Therefore, our goal for this project was to perform a fault detection and diagnostics in commercial office building HVAC systems using delta T. Delta T is the difference between supply air and return air temperature of the air handling unit in the HVAC system. The ideal range of delta T in cooling mode is between 16 to 22 degrees Fahrenheit. However, factors that could affect this outcome includes fan deterioration, air duct leakage, indoor humidity, and airflow. And instead of feeding endless variables to a software for calculation, we decided to use a more direct and simple approach for early system fault detection. First, we explored the metadata of the 200 buildings from which building 146 and 286 was selected for their relatively complete AHU sensor data and their synchronous capture time. Secondly, we investigated the relationship of available data for each floor, resulting in a correlation matrix based on 4 variables related to delta T and HVAC system efficiency. We then used cluster analysis to visualize the time series data. This method organized the data into groups based on their similarities, allowing us to eliminate outliers and reveal data patterns. For example, the daily pattern analysis enabled us to understand hourly HVAC efficiency during the day. The floor-to-floor comparison analysis allowed us to point out floors within abnormal temperature patterns. And lastly, through building-to-building analysis, we were able to compare the system efficiency of 2 different buildings and learn from the one that has a better operational strategy. So the delta T method can be easily adopted by most buildings in the market, for it requires only AHU supply and return air temperature. It is easy to calculate. The main sensors that it relies on are temperature sensors that are already installed in most buildings. And the data is easy to collect and process without demanding sophisticated software and heavy computational requirements. So our use case can be used as a starting point when conducting the technical, economic, and feasibility assessments for converting to all electric indoor environmental solutions. While any of the following strategies can be considered for new construction, we wanted to focus more on applying electrification and decarbonization strategies to existing office buildings. So to avoid any faults or leakages in the AHU and extra costs in fixing the operational systems, certain retrofit solutions that we think would help in the long run are considering strategies to minimize the amount of reheat needed to serve individual building zones that can tremendously avoid extra costs. Also considering hydronic heat pumps if the air handling units are supplied by a hydronic loop with a gas-fired boiler. So in conclusion, the delta T method is a quick and simple way for early fault detection and in building HVAC systems with easy implementation and affordable initial investment. And in terms of future work, increasing the sample group could increase the accuracy of the outcome. Adding a more detailed description of the data, such as room number or floor number, could also help in having an accurate outcome. Also, a large building database for benchmarking and resource pooling between building managers. Thank you.